Imagine that you are an alien that came from very far and you landed on Earth here in Australia, from Mars, say, and you're looking around. What do you see? So you look around and first of all you see there are lots of people, 7 billion people. They have lots of problems actually together. It's a very complex society. And if you look further around, you're actually pretty amazed because you see these inhabitants on Earth, what they have developed. It's arts and culture, sports, technology. It's actually a pretty advanced society. So you're rather surprised to see, it's pretty amazing what these inhabitants on Earth, what they have developed together as a society. What you also see, again, being the alien walking around, is that to run this incredibly complex society, it costs a lot of energy. These people on Earth, what they have? They have they heat their houses with natural gas, and it turns out they drive cars on gasoline. It's very advanced. They have coal that they burn to make electricity. They use, heat, as said, gasoline, electricity. They have a whole network of electricity, quite advanced. All their hospitals and their public transport, it's all in a whole network of electricity. It's pretty amazing, right? But it's all about energy. Everything is connected to energy. And if there was no energy on Earth, then this whole amazing society would just come to an immediate standstill, right? No energy, nothing of the luxury or the high-tech technology that these people on Earth have developed over the years. And so you wonder, again, as the alien looking around, where do these people on Earth get their energy from? And you look around, and you're pretty amazed. For example, what they do? They dig a big hole in the ground, they call it a coal mine, and they take out all the coal, and then, the coal goes in the train, and then it's traveled around the country, and it goes into an electricity plant where they burn the coal, and then they generate electricity. It's pretty advanced. There is something with the coal that generates all kinds of, stuff that goes in the atmosphere, and it pollutes the environment, but that they don't care about. Okay. That's something else they do, for example. What they found, if you drill a hole in the Earth crust, and you go 4, 5, 6 kilometers deep, there happens to be oil. And what they do is they pump out the oil, and then the oil goes into a big tanker, and that travels, around the entire globe even sometimes. And then they take out the oil, and then it goes into a factory. It's called a refinery, and they change the oil into gasoline, and the gasoline goes into another truck that then drives the gasoline all the way across the country to a gas station, where then these people on Earth that drive cars take out the gas and put it in the car, and this is how they drive. Okay, pretty advanced. But again, if they use all this gasoline and they burn it, it goes into the atmosphere, and it turns out actually the climate on Earth is changing so much that the temperature goes up, right? But they really don't care, right? They just need energy. Right? One more last example. This is the most advanced one you find, this again being the alien on Earth. What they do is it's kind of a nuclear bomb. They put in a building, they call it a nuclear reactor. And then they burn uranium, and then they create electricity. Again, it's incredibly advanced, right? There is something with nuclear waste, but they have a very clever solution for that. Because remember that they dug those coal mines. Well, you can put the radioactive in the coal mines, and it's all solved. Okay? So it's pretty amazing what they do, but really, what you don't understand, why do they do all this very complex stuff if they have this? There is this star, it's already there for 5 billion years, that shines on Earth and creates energy to everyone here, so much that it's more than enough for all the energy this population here on Earth they need. Yeah? It's already there for 5 billion years, this big gas, ball of helium and hydrogen, incredibly hot, hundreds of millions of degrees. It's just shining there, it's 100 times bigger than Earth. In fact, it's so intense that 1 hour of sunlight is sufficient to generate all the energy that everyone on Earth uses in a full year. Can you believe it? 60 minutes of sunlight is enough to generate enough electricity, heat, or fuel. There's enough energy in that little bit of energy from the sun to power the entire planet. And therefore, as the alien again, standing on Earth, looking around, you wonder, why don't they do this? So, good afternoon. My name is Albert Polman. I'm visiting here today, Monash University, but I'm in my daily life working at the University of Amsterdam in the Netherlands. And I was thinking, okay, why don't we do this? You know, how is it possible that there's this incredible source of energy and we don't use it enough for all these problems that we create with all these fossil fuels that we burn? And so I was talking with my colleagues in the Netherlands, in Australia, in the United States, and you know, we're making a plan together. There is a plan how to do this better. And what I would like to do this afternoon is to explain to you what that plan is. And the plan, of course, is what do we need to do to really use the energy that's radiating onto us from the sun every day to make a planet that really runs on energy from the sun. And to explain that plan to you, I first have to tell you a little bit about light, because that source of energy is because it shines light on us. And so let me first explain to you a little bit more about light. So I have here a little light demonstration on my table here. And so if you go into our optical labs, the same here at Monash University, if you go into a laboratory that has an optical experiments, you will see a big optical table. It's, of course, bigger than this black table here. And it's full of lasers and lenses and mirrors. I have a laser here, I have lenses and mirrors and all kinds of optical components. And so the first thing I'm going to do to you is show to you is the laser. Let me switch it on here. I have a green laser over here, and it shines light. It goes across the table to this little mirror here. And the mirror bounces it back to here. And the first surprising thing, of course, that you see is that you don't see it, right? I'm telling you there is this laser here, but you know, I can hold my hands in it, you will believe me. But the light goes all the way across the table. And so let me make it a little more visible. So this is a better way to see light. You know, I find this pretty spectacular, don't you? I mean, you can wonder, what is light? This you know, bothers us every day in our laboratory. If we're light scientists, you know, there's this stuff walking or, you know, traveling over the table here. And you know, you can't see it, but it's there, right? It's just going here with 300,000 kilometers per second. It's incredibly fast. It's incredibly straight also. See if we can create more smoke here. You know, I am, as a scientist, I'm really fascinated by this. So I like to solve the energy problem, but the way I want to do it is because I just love this, okay? And so in my lab, if you ask me if we go in my lab and ask my colleagues, what are you doing every day? Well, I would say maybe we just play with light, right? But okay, we not play, what I mean with that is we try to understand light. What is light, right? And if we understand light, then of course we can use it in a better way. Maybe we can help it to solve that sun problem there, right? And this is what I'm going to tell you today. So, okay, here's light. And so what do we do in the lab, for example? And I can't demonstrate it all here, but you know, you see these light waves, they go over the table. You know, I'm already telling you, light is a wave. Okay, what does that mean? Well, there's something in the propagation of the light through the air here that is a wave. I can't demonstrate that here, but the light can show kind of wave behavior. And what we do in our lab, for example, is to stop the light waves. We make light of which the waves actually stand still. Or actually we make waves where the waves can actually walk backwards. So we do all kinds of interesting, funny things with light, just so that we understand it better. What else to say about light? Well, light is of course playing a very important role in your daily lives in many ways, right? I mean, light from lamps, the fact that we have LED, this whole new lighting technology comes up. I'm sure you're all, already replacing your old-fashioned light bulbs with LEDs. I mean, you should, because it's just so much cheaper in the end. It's all because of this technology. This actually is an LED. It's a very bright light source, just a little piece of semiconductor inside that emits light. It's fascinating. In fact, the Nobel Prize for Physics went to this discovery a few years ago. A Japanese scientist, Nakamura, he discovered that you can make these very efficient light sources. Oh, by the way, also the Nobel Prize in Chemistry went to a light discovery not so long ago. It was scientists that built a microscope that used light in a very special way so you could see very small stuff at very small length scales. And maybe the last example I want to tell about light is in my lab I have a colleague that has these lasers, but he has them in all colors. He has green ones, but he also has red and blue. And what he does, if he takes a green laser and a red laser and he shines them together, he makes blue light. Okay, so he sort of is a painter with light. He mixes colors and then mixes two colors to make a new color. Right? And so that brings us to the question: what is color? Right? What is color? I mean, here we see very nice. The one thing I like about this is how pure this color is. Right? In physics, we say this has the wavelength of light is very well defined. It's very pure. What is color? And so to illustrate to you what color is, I'm going to do another experiment. And so I have another light source here. This is just a lamp. It's just a halogen lamp, nothing special. And it comes out here as white light. So this is white light. This is what we're going to start with white light. And now what I have here is a prism. So prism is a piece of glass. It's very pure glass, and it's shaped into this triangle. I mean, you've seen this before. And I'm sure many of you have seen this experiment in high school earlier. And then I'm just going to repeat it for you. But what I'm going to do is I just put the prism here in the white light, and what we're going to do is I'm going to demonstrate to you. So there's a little puzzle here that we can actually see that the white light is actually split up in different colors. I actually think I can do better. Here we are. So I'm missing the blue now. This is also in real life, okay? If you're in our lab, nothing works the first time, always. Whether you're an electron microscopist, a laser scientist, nothing happens or works the first time. But look at this. Isn't this fascinating? So we come in with white light and I just go through this prism, but actually it turns out the white light is composed of all these different colors. They're actually very nice, don't you think so? I mean, it's very pure. This is yellow, green, blue, ultraviolet. This is yellow, orange, red. So here we are. We've just learned something from this experiment. Light, white light, is just composed of multiple colors. Okay. Now, I am not the first one doing this experiment. In fact, Isaac Newton in 1668, and it's shining in your eyes. Huh? So let me. Okay, I'm gonna see if I can do this differently. It's not dangerous, but I just don't want to. Is it okay for you? It shines on your. Yes. Okay, thank you. So Isaac Newton in 1668 was doing exactly the same. He also had an audience like you, just interested in science and just wanted to figure out how stuff works. And of course, he did not have the halogen lamp, but he did this on a sunny day, and there was a curtain, and he had a hole in the curtain, and just the sunlight would come in. And he took this very same prism and he split light, and he saw white light is composed of multiple colors. Here we are. Okay, why is this important? Because that was the problem we had to solve, right? Okay, so why is this important? Well, this is an experiment splitting light with a prism, but the same is happening in the sky when we have a rainbow. If we have water droplets in the sky, if it's raining, then there's this beautiful rainbow of colors. And so look at this. That means that the sunlight shining on those little droplets that do exactly the same as this prism, also the sunlight is composed of multiple colors. Okay, so that's a very important realization. We have a picture there. This is a nice sort of red, image of the sun, zooming in on sort of solar flames. That's not so important. In principle, the light from the sun is very bright white, but in fact, what we know now, it's composed of all these colors. Okay? So then, if that's the case, let's make a bigger rainbow of colors here. So here we go. Here now is the colors from the sun. Okay? This is the spectrum of colors that is composed, or this together is making this white light coming from the sun. So It's very interesting. So what does this mean? I mean, we see all these colors here. So first of all, we should realize light means energy. I have an energy meter here. It's a very simple device. If it sees light, it will click. It's hard to hear, but this is my energy meter, and it tells that, in fact, all these colors from the sun, they carry a certain amount of energy. With energy, we mean what you know. Like if you have a lamp, it has watts. If you have an electrical equipment, it uses watts. The sunlight provides watts, energy. Okay. So this is going from red all the way to the ultraviolet blue here. But in fact, it turns out there are also colors here. I don't have them in my light bar here, but if there could be colors here where also if I put my light machine there, they also generate power. But you can't see them with your eye. It's very important because in physics and science we deal with this color spectrum, but then all the way to the left and all the way to the right. In fact, this is green and this is blue, but there are also colors here on this side, in the ultraviolet, right here, that you cannot see with your naked eye. But they're there, and the sun shines on you every day, very bright in ultraviolet. That's why you get burned, right? And the reason, of course, you get burned is you don't see it, you don't notice it. But the sun is shining ultraviolet light on you. It's there, but you can't see it. In fact, I could walk a little further here, and if I go a little further, there's also light here that you cannot see. It's called X-rays. So if you have an X-ray made in the hospital, it's nothing else than somebody is shining light on you. But that's the kind of light that you cannot see with your naked eye, but it's there. Yeah? We call it X-rays, but not, it just makes it complex. It's not necessary. It's just light. Right? In fact, I could walk to the other side here, and then beyond the red here is infrared, which you also know. Infrared light carries, heat. If you have something hot, it radiates. You don't see it because it's infrared light, but it's there. It's light. And then if we, would go even on further here, we have microwaves. If you have a microwave oven, it's also generating light to heat up your food. We have, microwaves going onto radio waves. There are all kinds of waves here for your wireless internet. It's just light. Yeah? So, light is everything. And what is, there's so many aspects of light, what I mean to say. But it just happens to be that only this small section here of light is what we see with our eyes. And so why is that? Why don't we see all this microwaves and millimeter radio waves, and why can't we see the X-rays over here? It's just fantastic. It's evolution. Evolution has developed our eyes over hundreds of millions of years so that our eyes are just sensitive to exactly this color spectrum, because that's the colors that the sun radiates on us every day. Okay? So it's not a coincidence that our eyes can just see these colors and the rest we perceive as invisible. Just because evolution has made us sensitive to what the sun shines on us every day. So if the sun was another sun that was, say, if it would be hotter, the skin of the sun is 6,000 degrees. If the sun was a hotter star, maybe 12,000 degrees, it would actually radiate not light in the red here, but it would radiate here in this invisible part. And I bet then human evolution would have caused our eye to adjust that it actually can see these colors. But that's not the case. This is just the temperature, determined by the temperature of the sun. These are the colors we see. Okay, so we're making progress because we wanted to use the energy from the sun to generate electricity. I'm saying electricity, I should say energy, energy that we can use. I mean, it should be clear. What is energy? We use electricity, we use heat, and we use fuel, right? These are the three forms of energy that we have. Electricity, heat, and fuel. And in one way or another, they can all be made using energy from the sun. I'll show you. So, sun is giving white light. White light is different colors. So if we want to use the energy from the sun in a clever way, we have to deal with all this whole range, this whole broad range of colors. Okay? And that is not so easy. Okay. So, now we're going to make a switch from understanding light to how we generate light from the sun. So this is a solar panel. You all know these things, right? You may have them on your roof. You've seen them in the field. These are little panels that, they catch the sun, and on the back side there's just 2 electrical wires, and this is just like a battery, right? You shine light on it, and then it generates electricity. And electricity, this we can connect to our electricity grid, and this is how energy from the sun is used. Now, how did this, beautiful technology, how did it evolve over time? Let me explain that to you first. So, it started in the 1950s when in the United States there was a company, a phone company, AT&T Bell, and they had to make the phone links in the United States from the East Coast to the West Coast. You've seen these, right? You have these wooden poles, and then there's these wires, and then they go through all the desert. They make these very long, thousands of kilometers in the end, electrical lines that bring phone signals from one place to the other. But as it turns out, if you do electrical signals over these phone lines, after every 30 kilometers or so, the signal has died out, and you have to amplify it again. So every 30 kilometers on the top of one of those wooden poles, there is an electrical amplifier that has to boost the signal, and then it go on again, another 30 kilometers. And to give energy to the amplifier, you need a battery. So every 30 kilometers on top of the wooden pole is an amplifier with a battery. But after 2 weeks, the battery is dead, right? And in these situations of putting all this in the desert, you cannot replace the batteries every 2 weeks. So the engineers of Bell got the assignment, fix it, solve, be clever, invent something to solve this problem. And what they invented was the solar panel. And it didn't look like this big one. It looked like, here, this little tile. Actually, going to make it a little more light again. So this little tile, that's what the engineers of Bell Labs invented in the 1950s. It was the first silicon solar panel. Again, a little piece of silicon. This is made out of the material silicon. And there's a front, wires here and wires on the back, and this generated electricity for the telephone boosters. It was not very efficient. The efficiency was 6%. That means that of the energy radiating by the sun on this little plate here, 6% was actually used to charge the battery. But not so bad, right? For the first invention that, you make something and it creates 6% efficiency. This was 1954, an invention of the silicon solar cell. And then, interestingly, this technology was developed further because of the Cold War. So the Cold War between the Americans and the Russians was fought in the sky, right? In space, because that's where you shoot your satellites and then you can spy on your enemies. And, that was the war, was figuring out who can do this technology fast enough, faster than the other. And the next development in this was that the Americans figured if we can shoot a satellite in space, but then after 2 weeks the batteries die. So if we put this on the satellite, we have a satellite that can just, go around Earth forever and it will always be charged, right? And so they did. And I have a replica of it here. This is the replica, it's a true size, of the Vanguard satellite launched in the United States in March 1958. And you see these little squares on here? That's the little solar panels that gave energy to the battery that was inside. And then this was a receiver inside that could receive radio signals, and it could also radiate radio signals back to Earth. Okay, 1958. Amazing technology. It's interesting to note, this is the real size, so how small this was. This thing, launched in 1958, by the way, is still orbiting in space. So it's the oldest object that's still circling every day around our heads. It's the Vanguard satellite. It's the oldest object that's still circulating in space. So that was 1958. And now we're here. So now we have this technology. And the big improvements that have been made over the years, that when this was 6% efficiency today, if you buy a solar panel and put it on your roof, it has 20% efficiency. So this material was improved in such a good way that the light, the energy shining from the sun on this, converted into electricity by these wires, is now 20% of the energy is converted. Okay, so that's nice, you would say. But of course, we as scientists were really unhappy, right? This is really disappointing. If only 20% of the energy goes into useful energy, Where is the other 80% going? Well, and we have to always conserve energy, so it has to go somewhere. It's heat. So solar panels just get hot, very hot, and all the energy, 80% of the energy just creates heat that we don't use. Only 20% makes the electricity. So we as researchers, that's what we want to solve. We have to crank up the efficiency. We have to go from 20% to 30 to 40 or maybe even more. Right? And so that's, if we want to make solar energy more profitable and then make it cheaper, this is step one. We have to make these solar panels 2 times more efficient. Okay? That's one thing. And now there's one other thing we have to do, and that is, this is pretty expensive to make. So it would be nice if we could reduce the cost by a factor 2 or so, if we make this 2 times cheaper. In fact, if we could make it 2 times more efficient and 2 times cheaper, then we're there. Then solar energy has become 4 times cheaper than what it is now. And then it's become so cheap that it's cheaper than all the other forms of energy generation that we right now have. Right? This is a very important number to realize. If solar power can be made only 4 times cheaper, it will beat coal and nuclear and oil, gas, everything. Okay? And that price is just so important because, okay, you may worry about the environment and you may worry about global warming and CO2 and all these things, but that's not the reason what we're going to change. In the end, this is not going to convince a majority of our population that we need to change the system. The only way we can win is economically. We just have to make it cheaper, right? Then everyone will want to do this. Okay. So this is our assignment. This is what I'm going to explain to you now, is what do we need to do to make this happen, right? And first was to make it more efficient. The other was to make it cheaper. Okay, so to do that, let me first explain a little bit more in detail how this works. So this is just the silicon, let me show it with this one here. The silicon, this is a silicon solar cell or solar panel, it's all the same. These little cells form together, form a panel. And as I said, it's a little piece of silicon. You see these wires on top? This is the electrical top contact. There's a big wire on the back. So this is just the plus and this is the minus. This is just like a battery, right? So it's just, if you shine light on this, it gives 1.5 volt, exactly the same thing as a battery, right? But this battery never dies, right? Every time you shine light on this, it will give electricity, right? 1.5 volt, and actually the current is 3 amps. If you're a specialist in electric engineering, it's a 3 or 4 or 5 ampere sometimes coming off this little tile. Pretty impressive, okay? So this is how it works. So, okay. Now one thing we had to do is make this cheaper. Okay, how are we going to make things cheaper? Well, this is a pretty expensive little tile of silicon material. Silicon is a pretty expensive material. So what would help is if we make this thinner. If we could make this much thinner, then we use less of the silicon material. Okay? In our lab, we just like to take a big step. So let's say, ask the question, can we make this 1,000 times thinner? Okay? That would be nice. Okay? Then it's just, the price of silicon is negligible. It's hardly costing anything anymore. Okay, but now, if we do that, and we can do that, now we have a problem. Because what happens, if I make this little tile very thin, and I shine light from the sun on it, what will happen, it's so thin, the light will just go straight through. Right? You need a certain thickness of this material just to catch the light from the sun. And if you don't have the thickness, then light will just go straight through. Okay? So here we have a dilemma. We would like to make this really thin, and therefore cheap. But if we make it too cheap and the sun shines on this, then the light is just not caught, it's scattered out or going straight through. It's not efficient. So now we have a problem to solve. And I'm going to explain to you how we solve this problem. And to do that, I'm going to show you a little movie first. I know this looks pretty mysterious. Okay, I'm going to show it to you again. What we're doing here, I'm going to repeat the movie. What we're doing here is we're zooming in. Let me repeat it. We're zooming in at the surface of a euro cent, a little coin. And that's a few centimeters across, and we're going to zoom in with a special instrument that is called an electron microscope. And we're going to look into one of the very small features inside this little coin. So here you see it was 2 centimeters, and we're going to zoom into this little star on the surface of the cent. And then in the star, you can see right in the center, there's this little square there. That's not there, by the way, if you just have a euro cent, but we made it in our clean room. We made this little pattern, this little field of little particles, and we're zooming in from the centimeter scale to the millimeter scale to eventually a scale that is even, 100 times smaller, 1,000, 1,000,000 times smaller than a millimeter. And so here we have zoomed in with this electron microscope at the surface of the cent. So if we would look with our naked eye, we would not see this. If we would look just with a standard microscope we use in biology class, we can't see this, it's too small to see. But our electron microscope can see this. These are little particles that we made with a special etch machine. I'll spare you the details, but we made these little particles in the surface of the cent. And the scale of this is 100 nanometer. Okay, nanometer may not mean much to you, but we have a meter, and we make it 1,000 times smaller, we have a millimeter. And if we make it another 1,000 times smaller, it's a micrometer. And then 1,000 times smaller is a nanometer. Right? So here we've gone to that nanometer, 100 nanometer scale. Right? So, it's very hard to imagine what it really means. So the size of this is about 100 nanometer. And, if you take the size of a hair, a human hair, for example, it will be 1,000 times thicker than this, right? 70 micrometers. So this is really small. And the reason I'm showing this to you is just to make you realize there's a whole world, a whole nano world that exists that you cannot see with your naked eye, but it's there, right? On the scale, on this very small scale of stuff, it can be anything. It can be this scent, it can be, this table, it can be your skin. If you would zoom in, there's a whole world of structures and interesting features that you cannot see with the naked eye. And it's interesting because we as humans, sometimes it's easier for us to recognize what the big scales are, right? We know what a meter is, it's the human scale. We know what a kilometer is, we can walk it, in 15 minutes or so. We know what if we go a kilometer, we go 1,000 kilometers. Okay, even within Australia, you can get quite far away, 1,000 kilometers. Make it 1,000 times bigger, 1,000,000 kilometers. Well, that's like to the moon, back and forth, roughly. And then we make it bigger, we have the Milky Way, we have the stars. The big scale, somehow we can imagine. There's a whole world there that we don't really know well, but we know it's there, right? But the same is true if you make stuff smaller. Go from the meter and the millimeter we can still see, go to the micron that we can just see, go to the nanometer that we can't see. In fact, your whole body is made out of this nano stuff, right? If we zoom in on your blood vessels, on your skin, on your nerves, they're all made of structures, they all work because they're made on the nano scale. And I'm telling you this in so much detail because the nanoscale, that's what we do in our lab. We try to use the nanoscale to make new things, new features. Right? And we're going to use nanotechnology now to solve this problem that we had with the solar cell. Because, remember, we had the solar cell here that was too thin, so it didn't absorb the light well. And now what we're going to do is I have a foil here. It's a nano foil. So this is a piece of plastic, and if I would zoom in my microscope, it would look like that. Right? So on the surface of the foil, we have made these very small nanoparticles. And what happens now, if I take my solar cell and I put my foil on the surface, is that the light comes in, it's catching, it's interacting, it's hitting these little particles, and the particles help to catch the light and keep it inside the solar cell. So the nano pattern helps on top of the solar cell. The light that would normally go straight through or catch out is now scattering against these nano structures at the surface, and they, you know, they can sort of stop the light and make it sit on a certain position, or it can make a right turn so that it is moving in this side in the solar cell. This is actually also good because then it gets absorbed really well. So this foil can really help catch the light inside the solar cell. So that's nice, because then in the end the solar cell will just become a foil. Right? Isn't that fantastic? If this would turn into something as flexible as this, because if it's this, then you know, you can integrate this in your roof tiles. You can stick it into the walls of your buildings. Maybe you can even put it in your clothes, your backpacks. If it's flexible, you know, it can go everywhere, right? So this could be a solution of our first problem, right? The problem was, how can we make stuff thin and still catch all the light? The solar cell will become a foil. I'm predicting to you that this is going to happen. Right? Become very flexible. Okay. So remember, we had two problems to solve. The solar cell had to become cheaper and more efficient. And the cheaper we have now addressed here, right? I think if with this nanotechnology we can make foils, and the foils can be made in a very cheap way. Okay. Now the other problem. So why is a solar cell only 20% efficient? So why does this little tile only converts 20% of the energy from the sun? The reason is, if you look at the solar spectrum, that this little tile is only efficient for the red part of the solar spectrum. So it turns out the property of this silicon material is so that it catches the red light very well and converts it to electricity. You know, so silicon is really perfect for red light. But remember, you know, we have to deal with all these colors, right? So we can't solve that with just this material. Silicon will be nice. The roof tile panels that we have now made out of this silicon material is fantastic. But since they only work for red light and we have all these colors to deal with, we're stuck. Right? Of course, you know, we're working really hard in the labs to make 20%, 21, 22, maybe, you know, 25. But this will never make 30, 40, or 50%. Okay. So now, how do we solve that? Okay. So we have to deal with all these colors. This stuff only does red, so we have to rethink, right? Forget about silicon, or don't forget, because we need it for the red, but we need to think about other materials. Right? And so now I come to my materials table here. And so now actually, we were optical engineers, now we're going to become chemists. Okay, I'm now going to be a chemical material scientist for you. And so let's see, to do that, here you can really see I'm coming from the Netherlands. This says periodiek systeem der elementen. You can guess what this is, you know, periodic system or table in English of elements. And if you're a chemist or a material scientist, then this is your menu, right? This is what you have to work with. This is, if you want to make new stuff, all the stuff around us is built out of all these elements here. And it looks very complex, but you know, that's because all the acronyms here. But you know this. I mean, we have just talked about silicon. There's oxygen here that we breathe every day. There's carbon that made the foil I just showed you. All kinds of metals here, silver and gold. They have funny names, Ag and A. There's all kinds of historical reasons. But just all the matter, all the atoms that we have to make stuff of, they're arranged in this table. Okay. And this actually is a very interesting history. This was a Russian scientist, Dmitry Mendeleev. He figured this out in 1880 or a little after that. He was born in Siberia, and then his mother sent him to St. Petersburg to study chemistry. And he was just playing with, you know, all kinds of elements that they dug up from the ground there, and he was weighing them. He had a weight scale and made the weight of different elements. And what he found is there was really a sort of characteristic rhythm in what the weight was of different metals. And one metal was sort of light, and then came the next was a little more heavy and more heavy, but there was nothing in between. It was just all these, there's sort of very characteristic weight steps. And he was a card player. He played a game called Patience. And you know, if you're a card player, you like to order stuff. So he, in fact, that's what he did. He ordered sort of the elements that he dug up and played with as a, you know, junior chemist into cards. And this is his card organization. Right? And he was able to, you know, put some of these metal element dots here in this chart, He also had white spots. This is elements that he didn't have there in Russia at that time. But he didn't have them, but he predicted they would exist. Right? Just because of the ordering that he made, he could predict the existence of some metals that were never seen before, but he could tell they were there. Okay, very, very strong, right? I mean, just for a junior chemist at that time to make this, because now, by today, we have filled in all the little holes. Yeah. There's still people looking for, can we go further? And yes, we can, and it's very complex, and these atoms fall apart. But this, now we know, and this is our table of, again, it's the menu we have to work with. So if our goal is to make new materials to catch all these lights, this is what we have to work with, right? And so here is silicon. So let's see, let's stay close, right? We can, what we can do is, for example, you can see silicon. This is in this column here. We can use gallium, for example, or arsenic as indium, aluminum, phosphorus. All these elements we can now play with. I see copper, zinc, cadmium. So this is what we're doing as material scientists. We sort of stick together all these elements, right? And so how do we do this? Well, okay, let's see how this really works. There's my foil. So here is, let's see. So here, let me start with silicon. So we were talking about here's a silicon atom. Okay. So what material scientists do is they build silicon atoms into crystals like this. This is a very old-fashioned crystal model. So this is every little dot here is a silicon atom. So if you would zoom in like that into our silicon solar cell over here, where is it? If I put it in the electron microscope, then if I put it in my microscope, then my microscope's not strong enough to see this, right? But to really see this structure. But if I would go 1,000 times smaller than that, and then it actually looks like this. And every silicon solar cell is composed of these little balls, and they're stuck together in this very nice rhythmic structure. We call this a crystal. And it's a crystal when all the atoms are sort of aligned in one direction. Then it's a good crystal. And the reason silicon solar cells work so good is because we can make very good crystals. Okay? So remember, the silicon atoms, if we stick them together to form a solar cell, here's one and here's another. If we stick them together and we form the right, crystal structure, we have the perfect red solar cell. Okay? That I told you with my color spectrum over there. So now we're going to play a little further. Let's say, look in our periodic table. What do we have? Here's cadmium. And cadmium turns out it can make a very interesting compound with tellurium. And so both elements in the periodic table, and we can mix them together and we can let them form a thin film. And if cadmium and tellurium react together, we have a material that actually catches the green light from the sun. So cadmium tellurium has a special property, different than silicon, that it can absorb green light and efficiently absorb the green light and turn it into electricity. Okay? And this is actually very simple to make. So people that make cadmium telluride solar cells, they basically have a foil like this. And they have a little crucible, they heat up cadmium and they heat up tellurium, and it heats up and the vapor just condenses on this foil, and they have a cadmium tellurium solar cell. Right? Okay, that's only one color. Let's see, what else do we have? This is gallium and indium. And I happen to know if I add phosphorus, here we are, then gallium indium phosphide is a very interesting material because, so now you have to guess what is the color of a gallium indium phosphide solar cell. Okay, we're going to do something else first. Here is copper, indium, gallium and selenium. And I can make a compound of copper, gallium, indium, selenium, and that makes the perfect yellow solar cell. Okay, so I was going to say gallium indium phosphide is also a very interesting material. It can be grown as a very high quality single crystal. It doesn't like to give light today, but you will believe me that this is bright blue. Okay, this would be the perfect blue solar cell. And also this material can be made even with a wet process, like two liquids that contain all these elements. You can mix them together and then they settle down and they form a thin foil of copper, indium, gallium selenide. So you see, that by clever use of this periodic table, taking different elements and grouping them together and make new elements, new materials, we can actually catch all the different colors from the sun. Right? So now we're nearly there. Because remember, we had this solar spectrum over here with all the different colors. And the silicon will be used to catch the red light. And then for every different color, we can develop a material to catch the right color. Now, it's very easy for me to say that to you. We just make this stuff and then we're done. But it took 40 years to grow silicon crystals to such a high quality that we can make the silicon solar cells that are 20% efficient. Now, I'm not saying it's going to take 40 more years before we can develop all these other elements to make them so pure and so crystalline. It's also not always necessary. And we learn a lot from the silicon technology. But this is what materials scientists do in the lab every day. They're sort of playing with atoms and sticking them together, finding new ways to deposit them, to evaporate them, to build these materials. I can tell you this is really tough. It's really tough. In a way, this kind of research is more complex than this, I could say, because somehow the optics, we have theories for optics that we can test, but the theories are very advanced, but we understand them. But we have no theory that can tell us exactly how we should make this material. And it's a lot of trial and error. We have theories that can help direct us, and we have technologies that can help test us and measure the crystal structures. But to really do it right, this takes a lot of effort. And that's why a lot of scientists, thousands of scientists today, are working on these materials. Okay, are we done? Well, we are, nearly, because we have a plan now. So we have a solar spectrum, has all these colors. We have different materials for every color. The only thing we still are left to do is we have to make sure if light comes from the sun, remember the white light, that in fact the red light is going to be directed to the silicon cell and the other colors are going to be directed to these other materials. And now, interestingly, our foil can still help. So let me do an experiment. Let me do two experiments with my foil. So remember I had my green laser here, and I told you in the beginning that if the foil comes and light comes in, it will redirect the light so it's stuck in the solar cell, right? So the foil is interacting with the light so that it gets diverted and absorbed in the solar cell. Here's the green spot going over the table on my white screen. If I put my foil inside, you can see the green spot is splitting up. So that directly shows that my foil can actually manipulate the light and sort of make it go different ways. Right? Now, I'm going to do the same thing with two colors. So I have a green spot here. I also have a red laser. So, switch off the light again. So remember, show it again. My green laser spot can be split by the foil, and this helps redirect the light in the solar cell. We can sort of make light make a turn. Now I'm going to switch off my red laser, and I'm overlaying my red laser with my green laser. So you can see here, it's hard to see, but I have a red spot and a green spot, and they're lying on top of each other. And now I'm going to put my foil inside. And you can see the foil splits the colors apart. Especially here on the left-hand side, you can see if I move the foil far enough, the red and the green spot, they're separated from each other. Okay? So that's nice. The two colors came in the same way, but this foil manages to bend away one color in a different way than the other. And that, in the end, is going to give our solution, because now we go back to our multicolor solar panel. We're going to just put the foil on top here. The sun comes from the top, and then the red light by the foil is going to be directed to the silicon solar cell, and the other colors are directed to each matching material. Or in fact, to make it even more advanced, and this is the final goal, this foil is going to be the final solar foil that both splits the light colors and also has all these different materials on the foil. So the final solar foil is going to be a flexible foil that's composed of silicon and all these other materials, little pixels that are all printed on this material. And there's a nanostructure, like there in the foil, that can direct the light to the individual materials. If we can do that, then we have all we want. We have a cheap foil, and it can have an efficiency. Well, remember, for silicon it was 20%. If we can do these other materials, we can maybe make 25, 30, 35, 40% efficient solar panel. So then we're there. Then we have a cheap and efficient solar panel, and then have we solved our energy problem? Well, okay, I said to you the factor 4 was important to make it competitive. And then what we do is we make electricity, right? The solar panel gives electricity. Electricity is what we use a lot in our electricity network. Electricity we can use to make heat, we can generate heat, right? We don't need natural gas to heat our houses anymore, we can do it electrically. To drive cars, well, we need electric cars, right? And in fact, there's also ways to use electricity to make fuel. So we could even, run planes on fuels that are made with electricity. So in the end, electricity can do everything. So let me end then by saying, is this practical? Is this going to happen? Well, first of all, we need to do a lot of research. It's very easy for me to show you that periodic table and build these little plastic boxes and say, okay, we just do this, right? But you have to realize that thousands of scientists, 10,000s of scientists all over the world, here in Australia, all over the world, are working really hard to get this to happen. Yeah. And I believe in it. I think we can do it. We just need to work very hard to make it happen, but we have the resources, the knowledge, we're intelligent enough to do it. And so then maybe the only final question is, if this is working, can we really make this at a scale so big, big enough that it can, we need thousands of square kilometers, to do this in the end. So can we actually have technology that we can, print out fast enough? Can we print this stuff fast enough? Well, that's the last thing I'm going to tell you. How would you do this? If you go here in Melbourne, if you buy a newspaper, the newspaper is made by a printing company. They have probably have five of these modern offset rotary presses. Right? There's 5 presses that run every day to print the Melbourne newspapers, roughly. Okay? If these 5 machines were going to be re-engineered, not to print newspapers, but to print solar foils, they would be done in 10 years. 5 machines are enough to make in 10 years enough foil to generate all the solar foil that we need all over the world to generate all the energy that we need. And so I think that's what we just have to do. That was it. Thanks very much.